Hi everyone. This is ME 5390 Advanced Thermal Design. Uh, Today I'm going to, we had a midterm. I'm still working on that, sorry. But today I'm gonna move on the chapter 5, chapter 6, a little bit first, and then chapter 5. Let me see. This is a totally different topic. So far, we have discussed the compact heat exchanger. Now, thermoelectric. Okay, thermoelectric. I think this course is the first time in this course ever I start discuss the thermoelectric because usually we had not enough time, so we could not reach that far. But anyhow, yeah, the before we talk about design, I'd like to a little bit talk about physics, thermoelectric, okay? Because I need a little bit talk about the background of physics, electron and photon and light, and then we can move on the chapter 5. Yeah, this is yeah, I'm gonna discuss, but let me first a little bit talk about the physics. Okay. So since you have the book, textbook, you have chapter 6, page 517, the physics of electron. And let me, can I, yeah. Yeah, the atomic structure, I like to, so the nucleus, I think the nucleus is a proton, maybe some neutrons, and then electron is kind of orbiting. So first we like to look at the just one proton, okay? One proton, typically same number of neutron, typically, but not necessary. Typically one proton, one neutron, and one electron, yes, possible. But the hydrogen has only one proton, and then it charged. Proton is charged positive, so that it attracts electron. So one electron, that is hydrogen. Okay, it's available. Hydrogen is available, and the electron is the a fundamental particle, I think, which means we cannot split. It's the smallest fundamental particle. But um, proton could have some quarks, possible 3 quarks. But it's a whole nuclear energy and we call proton. Okay, so proton. That's why there's a lot of energy. Proton holding proton. Again, the proton it forms a nucleus, usually a neutron, and proton again holding a nucleus. So it's involved nuclear energy. It's some huge nuclear energy. If you break it, energy is coming out, not only a proton, neutron. So when we look at the structure, it's very interesting. The nucleus, first of all, nucleus of a hydrogen side, the radius is so small, 10 to the minus 15. And then electron is orbiting, the radius is 10 to the minus 10, which means the hydrogen is vacated. It's a vacuum, nothing inside, nothing inside. Okay, that's very interesting. So the energy is quite conserved because there's no any foreign material to make irreversible friction, no friction, electron. So it's so weird, and quantum mechanics is quite a atomic. It is so weird. Okay, you cannot imagine. You cannot imagine. And we know the photon. First of all, photon is a particle. Is the light. Light is a particle and wave. So light is a dual property, shows sometimes a particle like a photon, and also the wave behavior, electromagnetic wave. So it's a wave and a particle. That's the what we understand. Sometimes it's a behavior particle. The electron is the same. Sometimes a wave and sometimes a particle. So that's the we understand. And the mass is so small, 10 to the minus 31 kilogram. And the proton is 10 to the minus 27. So it's about 10,000 times greater. Okay. So, and then what we are, this is the actually the photoelectric effect is we have to understand. Okay, what is there is some collector one side and the emitter, and so we connect and we can see the current, any electrons. If there's nothing happen, no electron, no current. But we try to put the light, some light. So some energy of light, nothing happened. Nothing happened, but suddenly a certain something happened. Okay, so electric current. We measure the current. So we had the difficulty to understand what happened. Why some light is not happening, but some light is a electron. If once is electron moving, we know that that's current. We can measure it. Okay. So we had a great difficulty to understand this um, since it was experiment was way earlier, Hertz, 1887, but we had a difficulty. And then finally Einstein, um, Einstein, I think what is the year? I think 1905 something, I believe. 1905, yeah. Einstein. Einstein discovered photoelectric. What he says, intensity is nothing to do. How strong intense light is nothing happen. The only frequency, a certain frequency, then light is coming, electron is coming out. So that he since he discovery of a photoelectric, the light is particle. That is only explained since it's a particle. Particle. Light is particle, and each particle has a frequency. Okay, so that's the energy of the particle. Then that is enough. The electron is moving. One electron is moving. Electron is everywhere. Electron is everywhere. So energy is matter of energy, certain energy, and then excite and the moving become electron is become free from the atoms. So this is discovery, and he received the Einstein the Nobel Prize about this. Okay, so photon and electron is the same. The wave, as long as it's a wave, particle, wave, dual property, and then energy. Okay, so H is a constant, Planck constant. So frequency, matter of frequency. Since then, since this electron is orbiting, is a wave, also particle, and according to, I don't want to go detail, but according to quantum mechanics, under subatomic particle behave wave and particle, and it can be anywhere. It's weird. The particle, it can be anywhere at simultaneously. That's very weird, quantum mechanics. Okay, so we don't know where it can be. No way we know. Okay, and then everywhere. That's why it's weird. Okay, so because there is no frictions, energy conserved, and then what happened is we calculate this is Schrodinger energy equations, and we calculated energy, and I don't want to go detail. It tells us something like a wave, something like a fundamental, and then second, third, like a string. You can imagine the standing wave, just two standing wave. It's something like that. Okay, so we call the fundamental is quantum number 1, quantum number 2, quantum number 3. That is the energy, because wave is energy. Einstein, keep in mind h and the frequency. So the frequency is energy. This is a wave, and frequency is energy. So this one has energy, actually, energy 1, energy 2, energy 3. There is no energy between these. No way we can describe energy. This is the smallest energy. That's so weird. So look at that. We calculate the n number of n, and the energy is just n, 2, 3. That's the energy, what we understand. Okay, so this is the energy around the nucleus. Okay, so this is hydrogen. Hydrogen, yeah, hydrogen. Hydrogen, the one electron inside the nucleus, so small inside nucleus. One hydrogen can be n number 1, n number 2, n number 3. So even one electron, this electron can be here or here or here. I told you there's everywhere. It can be anywhere at any moment. That's so weird. It's hard to explain, quantum. Students are so quiet. Are you there, students? Are you listening me?
Yeah, I'm listening.
Yes.
How many students? 12 students. Why we have 12 students? I don't know why. Anyhow, so this energy level is different. If this fundamental energy, if they receive energy, some kind of energy, light, I told you light, or thermal energy, or electric field energy, there's a number of energy, and then it can go jump to a second level, or even it can go to a third level. That's something weird. And then once it goes to third level, some receive energy, and then sometimes it is somehow it is lose energy and back to the second level. Then the energy must be the light energy, exactly same difference energy coming out. Energy. This energy is H frequency. So frequency is color. So this energy can be checked with the color. So this is evidence, actually. Where is yeah, there's a hydrogen. Some we can have energy. We can check the energy. This is energy, nanometer, and we can calculate the energy. And this is even we can calculate from where to where. You know, from where to where. Wow. So, so this color actually indicate the electron from high level of quantum number to low level quantum number. So this is a hydrogen. This is a hydrogen. But if we check the color and anything else, or even the human can see the color, but anyhow, the stars, we can receive some the illumination from the star. Then we can analyze what would be the element in the star, something like that. So basically, this idea is huge. This idea is huge. We can spectrum analyze, universe understand, and laser, even laser is the same idea almost. A laser is actually the laser. There is electrons, and then illuminate some. We control illuminate the frequency, illuminate light, and then excite, somehow control, and very strong laser we can coerce, and then we can control a laser, a very strong laser. The same. This is the same idea actually. Okay. Anyhow, so let's look at the silicon. Silicon. Yeah, this is a silicon, for example. Now, we try to understand the silicon, the atomic number is 14, which means 14 nucleus, 14 proton, and 14 neutron. So obviously, there should be 14 electron. So this is quantum number 1. This is quantum number 1. This is quantum number 2. This is quantum number 3. Different energy. Quantum number 1 and 2. Quantum number 2 is 1, 2, 3, 4, 5, 6, 7, 8. And then quantum number 3, 1, 2, 3, 4. So this, the uppermost quantum electron number, we call valence electron. This is the most possible, can be a free, if some energy and then become free, this energy from the silicon. So valence number is very important for each element. This is example is a silicon is 4, and copper, interesting, is a valence electron is 1. So only one is possible free. Gold is, it turns out the valence number is 1. Only one possible free electron. Anyhow, something like that. So because the second, this is so inside the huge energy, it is almost impossible the electron become free. The only a valence electron. Okay, so this electron can be free, and so actually the silicon, the crystal structure, silicon, the 3D, and then even crystal structure, you can almost the same as quantum number 1, 2, 3, and then become free. This is a example. I told you quantum number 3 is a electron quantum number, valence. So it's become free. And then conduction band. This is free now. Free. Okay, this is a structure. This is under structure. Something like that. Okay, so between the valence band and the conduction band, we call. So the gap. This is a band gap. So in order to become free, band gap energy of a band gap is a very important property, and then become free. Okay. So that silicon is a 4, 1, 2, 3, 4 valence band, and the phosphorus has a 3 valence band. No, 5. Phosphorus has a 5. So when we are doping into the silicon, one is more electron is available because of valence. Phosphorus has 5, silicon has 4, so one is left. In this case, much less energy, it becomes free very easily. So that the only electron can be free. Usually, in this case, electron is free, then there is a holes. This hole, the other can replace, and then hole is moving, not only electron. So electron is charged, hole is a positive charge, electron is a minus. One of interesting is you understand the electron is a moving charge, it causes current, but also the hole is moving exactly like a particle. That's weird. So positive is moving, also causing current, not only electron. But if energy coming and then one electron is free, then one hole is there, and then this electron can combine, and then nothing happen. So in this case, not much we can create the electricity. In order to create the electricity, we have to have a doping so that the electron, there's no way this electron can be combined. So that we can some control, and then we can have a current. A hole is again, the boron has a 3 valence band, so there is a hole naturally. So that easily some electron is replaced, and then hole is moving. Some hole is replaced, and then hole is moving. So we can control the hole. This is p-type semiconductor. This is an n-type semiconductor. That's why we need a p-type, n-type semiconductor to control over. Okay. I think just I'd like to give you some introduction about physics. Now we'd like to move on thermoelectric design. Okay. So here, thermoelectric is basically, let's look at it. Usually, the, the electricity is not easy to generate. Okay, some heat, energy, combustion, and the steam and electric generator, and then electricity. But this is thermoelectric is from material. For example, this is any material, and this is hot, and this is cold, and some thermal energy is enough to electron become a free electron possible. That's why we have a lot of electron or surrounding, a static. Um, we have electricity um, uh, everywhere, and so compared to cold side, one side is cold, the other side is hot, and then more electrons. Once is a more electron, this is charge, and electric fields forms. Once electric field is forms, and then the charge is moving under electric field. That's a Coulomb forces. So interesting is this electron must move toward the less dense area. Once the electron moves, then we have a current. That's a CVAC we call. Where is that? Yeah. Temperature, hot and cold, there is a voltage naturally. So this is coefficient we call CVAC coefficient. Okay, it's a small, but yes, temperature causes voltage. That was discovered 1821, Thomas Seaborn. That was so I was interested so early, much earlier than the electron discovered. So thermoelectric is known much earlier than the electron. Okay, and then so I said this is nature, temperature, and the voltage. But about 20 years later, Peltier branch discovered if there is a current, there is a heat flow. It's at that time, this was so weird. The current flow and the heat flow, which means actually the electron carries energy. I told you, electron is energy. Huh? Electron is energy, frequency, energy. Electron is particle, energy, according to Einstein. So that electron moving, current forms. That's the current. Current direction is the opposite direction of electron direction. Anyhow, once electron moving, current flows. Current flows. heat flows. That's Peltier heating, Peltier cooling. Oh, one side is heating, the other side is cooling. So interesting is once we have current, one side is heating, the other side is cooling. Refrigerator. We can have a refrigerator just to pass current. We can have cooling. This is so interesting. Or if you have a thermal energy, then we can have voltage and current. We can generate electricity. So we discussed the two things, Seebeck effect and Peltier effect. You can raise questions, students, okay? We don't, yeah, it's okay. You are learning, so if you have a question. Now, one more phenomena is Thomson effect. This is a different effect, okay? So what we found is if there is a temperature difference and the current, and then there is heat flows. In addition, Peltier cooling. So Thomson is so weird, so complicated. This is not easy, actually, at that time. That's why even though they knew thermoelectric effect, it was hard to apply, okay? And even hard to measure.
Is
Yes.
is that like a heat pump or something?
Yeah.
Is
Yeah.
it
Oh, yeah. Yeah. Heat
okay?
pump. Yeah.
It
Heat.
looks like the model of a heat pump where we have the Q high and Q low,
Yes.
and then
Yes.
okay.
Certainly. Yeah. Heat pump or yeah. I will talk about more later. Anyhow, now is uh, the physics. Okay. Phenomena. I'm talking about phenomena. Okay, now suppose we have a wire, one wire A, any wire A, and then wire B, and put no, this is later. I'm sorry. First, first this. This is wire A and wire B, just a different wire, and we measure the voltage. Okay, measure the voltage. And hot, one side is hot, hot. The other is cold, the other is cold. So according to voltage, A and B, because I'm saying A and B, coefficient Seebeck, and temperature difference. Okay, some say temperature difference. Temperature difference is a TH minus TC, something like the temperature difference. So hot and cold, and I think the sign is not correct. No, no, maybe correct. Anyhow, so a electron is moving. Do you understand? Say yes. Electron can be moving. more electron because of hot.
Yeah.
That's no problem. Here the same. Electron is moving. Yes? Do you understand? Say yes.
Yes.
So hot and cold electron is moving. So that suppose the more electron is moving lower side. I don't know, but depend. That's why A, B cannot be the same. If A, B is the same, it's canceled. But something B is more electron, so more current B side than A side. That's why the difference current is flowing. So in that case, there is a voltage flickering. It's very interesting. Just the wire, hot and cold, and the voltage created. No need electricity. Do you understand this or not?
Yes.
This is so weird. This is so weird. Again, hot and cold, and the voltage created. Current is flowing. So once it's current, it's a small, maybe, but once it's current, uh, and then voltage, what is the power? Power is a voltage times current, yes or no? Ohm's law.
Yeah.
So we have a power. Oh my goodness. That's the thermoelectric generator, or we calibrate um, the resistance, the voltage versus temperature, so that we can read thermocouple. This is a thermocouple. We can read C is reference, and then we can read the temperature. Thermocouple. Have you heard the thermocouple, TC? Yes or no?
Yes.
Yeah. Yeah. Everybody knows the thermocouple. The thermocouple does not need any the source of voltage. No, it generate millivolt generate with the temperature. So we measure the voltage, and the calibration obviously need, which means temperature measure, and calibration. Okay, the voltage. I'm sorry. Millivolt and temperature calibration. Once you calibrate it and measure the voltage, you can read the temperature. That's the thermocouple. Wow, beautiful. But A, B must be different. Okay. So if you look at thermocouple, one material A is something, the other B is something. Well, they can choose a good material. So we understand the thermocouple, and we understand the thermoelectric generator. That's the Seebeck effect. Now, we look at the refrigerator. Okay. Say AB, and then we put some battery and the flow current. Suppose we flow current. Okay. And then if current flows, it depends on the A and B material, but I told you Peltier cooling possible. One side is heating because electron electron is moving. Electron is moving. So energy, thermal energy, energy of electron, so many energy. Actually, 1 centimeter, 1 centimeter, 1 centimeter silicon. The silicon has 10 to the 23 atoms per cubic centimeter. Well, atom is so small, so 1 centimeter is so small. 10 to the 23 atoms at the room temperature, believe or not, room temperature 300 K. It is, we measured 10 to the 10 electron, free electron. Amazing. This is amazing. Silicon. So, and every silicon has so many electron is available because of room temperature even. 10 to the 10 out of 10 to the 23. So, for example, silicon, but any others are similar. So basically, the material A and B, what is a material A and B is A minus turns out to B. So if it is a plus, no matter how A, B, it's small. But suppose B is a minus, like holes. I told you, holes, alpha is minus. No, plus, I'm sorry. The hole, electron alpha is minus. So if we put the minus here, it become greater. So I think that's why the n-type, if you put the B n-type, A is a p-type semiconductor, it's a great idea. That's immediately we can see that. So we Peltier is easy to understand. Any question about the Peltier? Anyone? Peltier cooling heating is very easy because current electron carries energy, so that the cooling effect. Actually more than that, but basically. Now, so we understand the Seebeck, we understand the Peltier, but we try to understand the Thomson heat. That's a very difficult. What the Thomson is tau I delta T. Thomson tau I. So this is Thomson coefficient, tau, current, and the gradient. So, okay, then Thomson, what is that? Okay, look at that again. There is a temperature gradient. Yes, we know that. Law high temperature gradient. And also current. I said that we put the current. So we have a current. So that this is coefficient is always a positive. So would that be let's say this direction? This gradient is positive or negative?
Would that be negative? Or for the temperature gradient or the,
Temperature gradient. Here.
oh, would that be positive? Going from low to high? No.
Yeah, positive. Yes, you're right. Positive. How about the current?
That would be negative.
So this is positive. So total Thomson should be negative.
Negative.
So negative heat. This is wrong. I made it wrong. I made it wrong. I think anyhow because I told you AV can be anything. So this way. Plus minus. So it's a then it's a positive. Positive is positive is a positive. What is a control volume? Heat into is positive. Heat out is negative. That's the first law. So with the positive is into the, and then here is negative is out. So something is weird. The wire, not only terminal, wire has absorbing heat and dissipate the heat. That's the small, actually small, but that is so make experiment difficult. Okay, no way we can measure the temperature because of this. Okay, because of Thomson, so complicated. Experiment is so complicated. So that's why people have a difficulty to really figure out thermoelectric. It look like simple, but very difficult. Okay, now I like to summarize. The Seebeck and the Peltier and the Thomson, Seebeck Thomsons are reversible. Believe or not, reversible. Reversible, mostly reversible is hard to understand for students in thermodynamics. Most of a process is irreversible. No way we can reversible. Cooling, heating, friction, everything is irreversible. You cannot reversible. But this is electron. It turns out reversible. And anyhow, let's move on. So that the Thomson actually relationship This is the Peltier cooling, Peltier coefficient times current. So that the Thomson, the people have a lack of knowledge about thermoelectric. They mostly Peltiers and the Seebeck, but not much people know. But this is huge. Thomson discovered pi is nothing more than alpha. We don't have to put A, V, T, and the I. This is Peltier. This is Peltier now. Current, temperature. So Peltier. Peltier can be heating, cooling, but whatever. So this is originally this is Peltier. So Thomson's discovery is huge. Now we will discuss later. What time is it now? 5. The figure of merit is alpha square and sigma k. K is thermal conductivity, Seebeck, and electrical conductivity, or alpha electrical resistivity in K. So this was turns out the inverse of temperature. So G times T is dimensionless. If you multiply temperature, is a dimension is GT. That's why GT value we talk about. Right now technology about 3. No, 3. 1. The material. So we try to increase 3 in 10 years. So GT is a figure of merit. Is higher, the better performance. We will talk about later. And the materials, there are a bunch of materials. Look at that. Temperature and the GT value, and plot it. So that this is mostly room temperature 400 bismuth telluride p-type, n-type is the best, about one. This is right now technology. If higher temperature, some lead telluride, scudarudite, all kind of available, higher temperature. Okay. But the room temperature this is the best. That's the right now. We're going to have a break, 10 minutes. I will be back. Okay, thank you. I'm back. I'd like to continue thermoelectric generator and ideal equations, kind of standard equations. I had to give a name, so I would like to say ideal equation. Don't confuse it, ideal gas equation in thermodynamics. Yeah, anyhow. So the energy, not the energy, electric field, Ohm's law, according to Ohm's law, and current density and the electrical resistivity, or in terms of voltage and current and electrical resistivity. So Ohm's law. This is known electric field, but now we have electric field is the temperature gradient, Seebeck. So if there is a temperature gradient, the Seebeck, and this is associated with the electric field. So this is the, we're gonna use it. Mostly this is so small, so just on the law, but actually there is effect of temperature in the electric field. Now, the question is heat flow. Heat flow usually it's we know temperature gradient and thermal conductivity minus. That's the heat flow. Heat flow density we call. But the heat flow now, according to Peltier, we know that there is a heat flow. So obviously, this and this is heat flow. Now, okay, not only thermal conduction, but also Peltier. So we have it here, okay, and the electrical too. So combining this and heat diffusion equations and the steady state and heat generation is just, it turns out, in terms of, yeah. So that plug in, this is the heat diffusion equation final, including Seebeck. Now, we're going to solve this, but sometimes we have a difficulty. We can solve, but we have a difficulty. And also Thomson defined Thomson coefficient. What is a Thomson coefficient? Is temperature and Seebeck gradient with respect to temperature. If Seebeck is changing with the temperature, there will something Thomson coefficient turns out. So that this is I think a perfect, good. If we use this, this is exact solution. But this is not easy to figure out temperature gradient, etc., etc. So sometimes we neglect Thomson effect or assume the Seebeck property is constant. Sometimes it's not. But if we assume constant, then whole these terms is neglected. Okay, so and then also I like this is a module, commercial module. Usually, it's available in the market. They have a P-type, N-type, something we discussed, but this is a small temperature, so we need a number of couples. So many couples in a module, and then ceramic, the ceramic insulation, electrical. This is electrical conductor, so insulation, ceramic is required, something like that. So this is module commercial. You can buy $20, $30, or I don't know. It's a commercially available. You can buy, and but the unit couple, because the module is a number of unit. So just the unit we understand, and then multiply is a module. So this is unit couple, and this is N-type. This is N-type. This is a P-type semiconductor, and N-type is electron is moving. P-type is hole is moving. The hole is the same, hot, and the cold is more holes created, more electron is the same way because of energy, and then less, and then less. So that moving, hole is moving. Hot, TH, TC, and then we put some voltage or put some resistance, load resistance, and then circuit. This is a circuit. QH, hot side, QC is cold side, TC, and the electron should move, and then there is try to current moving upward, and the hole is moving, but the current is the same direction of hole. That's why it forms a current. Current is current. Okay, so hot and cold, it's something like what is uh, uh, yeah, something like electromotive forces created like a battery, something like. So its current is flowing. Okay. Now, what happened is Peltier. We understand electron is moving. There is a Peltier cooling, heating, and but there is a Joule heating. Joule heating is a I square R, whatever. So current and just creative Joule heating. Half goes up, half goes down. There is no directional. Half goes up, half goes down, Joule heating. This is irreversible. One more phenomena is conduction. High and low temperature, there is a conduction. Thermal conduction taking place is irreversible. So that we come up with uh, um, this is a Peltier cooling, heating. This is half against the direction of heat flow, the joule. This is a way I would say Peltier. I would say cooling. And this is a joule heating phenomena. And this is thermal conduction. So K is obviously K over AK over L length. So say this is the length of element, length, N side, P side, length, and A, area, A. So that the conduction. So three phenomena, ideal equation. This is ideal equation because we assumption we had to assume no Thomson effect, no Thomson effect, no neglect, and there is always a radiation convection heat loss neglect, and there is a conduction contact electrical and thermal contact resistance neglect. So, and the Thomson. So 1, 2, 3, neglect. So we have a small, but we neglect, and then ideal. This is ideal equation. Otherwise, it's very complicated. Even we don't know how much heat loss depend on the Seebeck. Thomson is very difficult to figure out how much, and contact is very complicated. How much contact we don't know, so we neglect, and we have ideal equation. Okay, although ideal, but it's a nice. We can discuss thermoelectric effect and the heat transfer. Even we can discuss with the ideal. And obviously, this R is consists of electrical resistivity and length and element N type and the P type. 2. So that's why K is the same, N type, P type, 2 altogether. So this is N, number of couple. Each couple has N type, P type. Okay, so keep in mind N is number of couples, and R take care of N-type, P-type, K N-type, P-type, A is N-type, A is AP minus AN, so that the couple. So this is a couple, and then N is a number of couple, must be total. So QC is similar, but a different sign, QC. So if we have um, this is a TH source pi, T low, and heat engine. So QH and QL, and we have network. So according to control volume here, QH is plus control volume, QL is minus, it can be a dot rate chain, is minus work net equal 0. Why? Steady state. We just consider steady, so no stories. So net work is always QH QL. This is what happened. This is what happened here. So QH and QL, and then we got this. And also the power is nothing more than power. Power is nothing more than the I and external I square. So this is the power here using external resistance. The R is internal. This is R internal resistance. The external is we call load resistance. I'm sorry. We name load resistance. Okay. This is internal resistance. So that just a simple thermodynamic using the internal, no, external. This is external load resistance times N. This must be power. And
Professor, I'm sorry. You said N. Is that just for all these N's? Are they all just the number of or the length or something? What is N for all of them? I missed that.
N,
Yeah,
number of thermocouple.
number of thermocouples. Okay, so thank you.
Number of
And that's the same for all the equations, right? That
yes,
have N.
yeah,
Okay.
number of thermocouple. So that we can calculate the voltage. And if you combine these two, and we can come up with this. This is beautiful current. It must be this equation. Current is nothing to do with the N is canceled. And C back TH minus TC over RL plus R. So that's the current we can calculate. And voltage we can calculate. And the power we can calculate. This is ideal again, but and efficiency, thermal efficiency is what would be the thermal efficiency over here? there is a QH, there's a QC, and power, net power, and efficiency is usually input over output. So what is the input in this efficiency business? Hmm? Can you figure out? Can you figure out?
The W dot N? Or what, are you looking for the output?
So what is input? This is a generator. What is the input of a generator?
Is that W net?
W net is the output.
Would the heat input, would that be the input?
I'm talking about input. What is the input?
QH?
Yes. Output, Q. Output is a power output. That's what I talk about. So efficiency is nothing more than the output and input and the plug-in and a little bit algebra. This is just I just yeah, using algebra, the same equation. It turns out function of three things: Tc over Th1, Rl over R is 1, and one more. Anyone figure out one more? Hmm? No? Tc, Rl, Rl, Tc, Rl, Tc. One more.
Is that ZT, 2ZT?
Yes. Gt is a function. Gt is a figure of merit. This is the temperature ratio. This is a resistance ratio, load over internal. So 3, okay. And then I try to generalize. That's my work now. Once we have a specific situation, we can discuss, but I like to generalize. So in order to generalize, it's not easy, but somehow I try to figure out maximum possible parameter. What would be maximum current conceptually in this situation? In this situation, what would be maximum current? Anyone? Possible? Hmm? What would be maximum current possible the
Would it be
mechanical.
voltage divided by resistance, or
This is optional. You can put any resistance, but we don't know. But so just I said R over R load resistance. Then current may change depend on the RL.
oh, when RL equals 0, then?
Yes. No. Yes. 0. It's short circuit we call. Short. No resistance. Short circuit. Then maximum. Yes. So that that's what I found. This is the maximum possible. How about the voltage maximum now? Voltage, maximum voltage possible.
It's an open?
Yes. Open circuit. So once you open circuit, you got the voltage maximum. It is actually yes. And then this is I have to little take derivative to get the extreme values, and then we got it. We have some take a derivation differential, because once we have expression for power respect to RL over R, and we found it. So maximum. So we got the maximum. And efficiency, again, take a derivative. We have efficiency expression respect to RL over R. We got this. So we have explained. It takes about 10 page. It's a lot of algebra. I spent about 10 pages. But anyhow, yeah, okay. So once we have that, then I was able to normalize actual over maximum, and current, actual current over maximum, actual voltage maximum, efficiency actual over maximum. I plot it. This is my work. I never seen other books. Okay, so this no, I'm sorry. It's I work, but my work is normalized. My work, but this curve has been seen. Okay, but not normalized. Anyhow, so this is power solid line in terms of resistance ratio. So what is the maximum power occurs when RL over R, when RL over R is what? Maximum power occurs. Can you read? Answer, please. I have to move on.
Let's say R equals 0.
Here?
Yeah.
Here is power is 0.
Oh,
I'm
well,
talking
I was
about the
looking at
maximum.
current is 1, I guess.
1, yes. 1 is, look at that. 1 is the maximum power. So that make a good sense. RL is a R is a whatever the module have R internal R property, but RL is optional. You can put anything, but the same RL over 1 is maximum power. That's a beautiful theory. And efficiency is a little bit more than that, but very close, about 1.5 in this case. Okay, then current and the voltage, you know, we can see that. This is, I use the TC ratio 0.7, GT1 I used for this. Anyhow, the only efficiency I need this and this. Others are even, I don't need these values. Look at that. Voltage is only function of RL over R. Current is only function of RL over R. Or power, even power is interesting. Power is only RL over R. Wow. This is ideal again. Okay. Ideal equation we used. So we assumed anyhow, not realistic, but ideal. Okay. Now, the same, but in terms of current, I can do that. In terms of current ratio, this is power, this is efficiency. So very interesting curve of power. 0.5, I think, exactly center, and the maximum power. Okay. And you can see ratio is 1 here. You can see that. So this is ideal, and I think I'd like to show you. Do we have time? Yeah. Hmm.
Professor?
Yes.
So is ZT strictly a material property, or
Yes.
it's just
Material
like
property. Yes.
how efficient the material is,
Yes.
basically? Or
Yeah, material property.
okay.
That's a very interesting. And this is a commercial. This is a commercial product. European, and this you understand this module, and well, I developed the maximum, but they are not using the maximum values, even they. So actually, my book is in advance than the industrial the people. So they are not using, but I can find it. The load means the load resistance have. They look at that. Load resistance same, they say. So this is the maximum current, our expression. And then this is a real, this measurement. Amazing. This is current measurement. This is power, watt for module. And this is what is voltage. Do you see this curve? Our the exactly half current. It's amazing. There is a agreement with the ideal. This is real, which means including. This is measurement actually. It should be a Thomson effect, contact resistance, and heat loss, everything because of measurement, real. But it turns out it's a good agreement with ideal equation. And the voltage, look at that voltage. So according to, let's look at again. I think you have to understand this is ideal. This is ideal now. Well, this is a general, the ratio, maximum current, you know. So the voltage, one means what? Voltage one means the voltage is the maximum voltage, isn't it? So that this current again, one means current is maximum current. Okay, now this is commercial. What would be maximum voltage now from real? Can you read for me?
Like
The voltage
14.
is red is the voltage.
Oh, voltage is like 11.
Yes. So the voltage maximum is 11 according to our analysis. How about the maximum current? Anyone smart? What is the maximum current?
Like 1.3.
No, that is the maximum power current, maximum current.
Output.
The current is here. What is the maximum current in this plot?
2.6.
Yeah, 2.6 or 7. Now, load. What is a load current? Maximum power is load.
That's 1.3.
What is maximum power? Anyone?
watts.
No.
7.8
No,
watts.
that's that wrong side. I'm sorry. That's 7 watts.
Yeah, about 7 watt. So this is our reading, but they say load is 1.4 load. Yeah, about close. Our uncertainty reading. Their load voltage is 5. Their power is 7.3. It's actually nothing more than just read it, you know, voltage, current. So this is exactly agreement, the shape. So once this is real, once we have a real maximum, they don't say, but we can see that, then do you think actual power? Actual power? Yes. Actual current? Actual voltage for load? Yes. You can calculate. Or any current. So that, because of the shape is, that's what once we know the maximum value, we can compute the actual value. Even efficiency. If you have a maximum. So now, interesting is the ideal equation, we don't know maximum. This is ideal, but the real, we know maximum, then we can estimate actual. Because of shape is the same, exactly, symmetry same. Look at that, voltage. Look at that. No change, actually, if you curve fit it, same. Something, the assumptions are small, not the small, but in terms of, not the small, no, it's a big difference. But if you know the maximum real value, you can figure out the actual value. That's a little you have to practice. Let me move on. What time? Yeah. So this is maximum efficiency and the GT value. We are using some kind of here reality, but we are looking for future 3. So right now is here. If ratio is 0.3 and here, so efficiency is small, 0.15, 15%, probably, or 10. But if you future material improve, GT value improve, then 30% is huge. Efficiency 30%, just the thermoelectric. What is the efficiency of gasoline engine? Anyone? Power, efficiency. Come on. Gasoline engine. No one knows?
Somewhere in the 30s, 36 maybe %.
Yeah, 30%, about 30.3. This is a gasoline engine. If you go 3 GT, it's just no, no piston, nothing, just combustion and temperature. It convert to 30% possible, ideally possible. Some indication of efficiency with the thermoelectric. Okay. I think there is a number of examples. You can look at it. I think you are smart. You can look at. I don't want to go over example. You can, once you have a concept and homework. I think 5.1, 5.4, 5.6 due next week, next class. I'm done. You have to go over the example problem and read, practice, and do homework. Any question?
Hello?
Okay.
Hello, Professor.
Okay.
Hello, Professor.
Yes.
I just wanted to say I've sent you an email. So if you read it, that's all I wanted to say.
Say again. I'm sorry. Say again.
I've sent you an email.
What does it mean? I'm sorry.
No, I'm just saying, like, if you could just read my email, I'll just send it to you. That's all I wanted to say.
About what?
It's about another class.
Another class. Oh, I will look at the email. Thank you.
Okay, thank you.
Okay. Any other questions? Bye-bye.